Hello, everybody. Hello and welcome. Welcome again to our online sessions. Today we have a special guest, Dimitri. Hi, how are you?
Hello. It's a great pleasure and honor to be with you. Yes, we've just made a small talk before this conversation. I believe it's hot where you are. It's hot, by the way, here as well, but I think we're gonna have a nice evening together.
Yes, thank you so much. So, let us give a little bit of introduction about firstly Dimitri. Dimitri is a well-known speaker, is a worldwide speaker, frequently speaking in the conferences, traveling everywhere. He's also a Java champion and also a very Helidon project contributor and lover. So today he's going to talk about virtual threads. So if you have any questions, guys, please post it in the comments below. And the stage is yours, Dimitri.
Thank you.
Good luck.
Yeah, thank you so much. Once again, as Moath is correct. Yes, I told your name. So as presented. Yes, I am. I've been working for Helidon for several years. I'm now currently a little bit enjoying sabbatical because I made 20 years of programming and I decided to make a small sabbatical. But yes, I was working and I was contributing to Helidon project very much. I really love this project. And yes, today I'm going to talk to you about virtual threads in action. What does that actually mean? Is not common information about virtual threads. Um, Oops, not sure, sorry, but slideshow. Not, common information. What is it? Why is it bad? And so on and so on. But I will tell you about how we use it, and you will see really how this virtual threads actually changed the world, I'll be honest. So that means that you'll see not only like something theoretical happening in the, some, world, like, um, um, I'll call it like this, so like a refined world of something academic, but no, you will see how they really work in action. And I'm really happy that we in Helidon project actually use them, and we are the first to use them in like real life projects. So once again, my name is Dimitri. As I tell you, I'm enjoying sabbatical. I'm currently based in Sofia, Bulgaria. We have just understood that this is like the same time zone, so it's very nice. And you may find me mostly in Twitter or X or in Mastodon. So whenever you have questions, whenever you want to find something, just chat with me, just write me there, tweet me there. I usually read this and try to answer as much as quick as possible. So once again, so we start. So threads, yes, threads is complicated. I believe that everybody who tried to read this very famous book by Brangos of Java concurrency in practice may have suffered a lot. I'll be honest, I was one of them. That means that everything about threads is complicated. Everything about threads is, I would say, really hard to understand or really hard to get used to, maybe. But we all know that reading these books, by the way, I strongly recommend you reading this book. And once again, the purpose of this talk today is not to go through threads and go through all of the basic. We don't have time for this. Our idea is to see how we actually use threads and virtual threads. So please go to this book, find it, read it. You will be surprised. It is complicated, but it really is, I would say, the highest level of programming you'll ever do. So this book is highly recommended. It's classics. Yes, and what we know from our experience that threads in Java are really expensive. What does that mean? So typically Java threads are just like wrappers over the operating system threads. That means that actually JVM is not that much managing them. It gives it mostly to the operating operating system, and to keep all the contexts and to keep everything running in these threads, we really need a lot of metadata, and threads in Java are expensive in all cases. That means that we need about 2 megabytes per thread for every memory consumption. And it means that if you start a thread, that you get minimum of 2 megabytes threads in your ROM just to keep the thread information. We need about 1 millisecond to start every thread, and just switching between threads is also complicated. It's also heavy operation depending on your operating system. It may take up to 100 nanoseconds, or maybe more, or maybe less. But yes, everything about threads is expensive. That means that we usually do this multi-threaded programming when we need to highly optimize our systems, and usually we hire the most expensive professionals to do this for us because it is complicated. Once again, if we take threads as they were before Java 21, or actually Java earlier versions, you can't even start a thread. Well, if you want to start 1 million threads on an infinite machine with infinite RAM, well, first of all, you will need several minutes just to start them. And then you most probably won't even be able to do this because all this garbage collection stuff, all this management stuff and JVM will actually take all of the resources just to manage them. So threads are expensive, and threads are something that is hard. It is what it is. Yes, and to do something with it, they have started so-called in Java, in Java community, in Oracle, and not only, they have started this research project called Project Loom, which is actually based on a very famous idea of using lightweight threads or fibers, or there are many other names of this thing. Not so many, but actually famous names about it. Well, we don't actually go to operating system threads, but we create our own structures which manage those threads, and they are this lightweight thread. So interestingly, they are familiar from other languages like Python, for example. They have this fiber, so .NET have them. Kotlin does have with coroutines. I was surprised that PHP does have them, although I have no idea how they use it. Actually, I have no idea how those people actually use PHP for multi-threaded programming. But even in Perl, we have this technology. I was surprised. I'm very much, scared of people using Perl because I completely don't understand how you code in Perl. But yes, we do have this technology. And so they have started this project with the idea to explore the fibers and continuations in Java. Yes, the previous name was not virtual thread, it was fibers and continuations. And yes, we have this name still kept in terminology of this project. And actually, for several years, this was a research project. Every Java have 4 to maybe 3 to 5 research projects happening in parallel when they test new features into JDK, and sometimes they get included in the main distribution of JDK. And yes, fibers and continuations were one of those. And what was actually the main idea? So several JEPs, Java enhancement proposals, were written, and after some years of work, they became available with JEP 2.425 and JEP 3.436. They have become available in different distributions of JDK, different versions of Java, but as I would say, preview or experimental features. Yes, that means that they were firstly developed, and then after JDK 19 available as experimental features. You can play with them, but they were not production ready. So what is actually the main idea? So here, unfortunately, I don't have auditorium with me, and I cannot ask you questions. But most probably, those of you who are familiar with earlier versions of Java heard about so-called green threads. Green threads were the technology to run multiple thread on one thread. And Project Loom is a little bit different because we actually start M threads over M real threads. And what is the idea? So virtual threads by API are the same as threads in Java, and they are some kind of like abstract structures which are mounted over real threads, which are called the carrier threads. Yes, JVM take care of all this for you. So when a virtual thread gets blocked, for example, yes, something like IO operation happens, yes, or I don't know, you call a database or network call has been. So JDK now knows about this points in our code which are usually get blocked, and it can understand that okay, this thread is blocked. We don't need to wait for it. So we unmount this thread from the carrier thread and make room for others. That means that the scheduler of the virtual threads takes what's another thread have like there's another thread waiting for something. It mounts it over and does the work, and whenever those previous thread is unlocked again, the scheduler will find a carrier thread and mount it over there. Yes, so there is a fork join pool used for this. That means that we are using these so-called work stealing algorithm. So whenever there is a work, so carrier threads steal the work from the others just to keep them busy. And the best thing is, once again, that they by API are absolutely the same as usual threads, which makes this very, very hard, very easy. Sorry, very easy to actually migrate. And yes, internally, it's implemented with continuations. It's exactly what I told you about fibers and continuations. The idea is that you have special places in the code when, for example, an IO operation happens, and JVM knows where the block is, and it actually makes like a snapshot with a continuation, a special structure, which is not like a thread, but it's a structure to keep the state of the work that happens now. And then it's been unloaded and mounted over another thread. So that means we are out of this situation when you have to think about, starting a new thread, switching between threads, all the operations I told you here. That's where is it? At this slide that we have to start a new thread with 2 megabytes memory consumption. We need 1 millisecond to start, and switching between is hard. Here it's not the same. Here we have this very, very lightweight construction, which is not a real thread. And it can, by this way, we're able to have millions. Yes, virtual threads can be millions, and you can easily start them and easily, throw them away. What is actually good, the idea that you can create a workload, a job, make it a separate thread, create this virtual thread, do the job there, and just throw it away. And it's not considered as a heavy operation anymore. We just have to know this.
Dimitri.
Yes.
Sorry, Dimitri. Can you please share your screen? I think your screen is not shared. Sorry.
Ah. Okay. Why didn't you tell me a little bit? No. Oh. Just give me a second.
It's good. It's good now. It's good.
Yes. Yes. Okay. So now I'll just go quickly through the slides. Once again, this is the first slide. This is about me. This is the book I was talking about. Java concurrency in practice by Brian Goetz. I told them about that we need about 2 megabytes per thread, about this context switches. This is the Project Loom. These are the languages that use fibers. This is how it was previously called, some jabs about it. And yes, this is the, once again, I'll just repeat it because we really need it. We have virtual threads, which are mounted over carrier threads. Virtual threads are just, abstract construction. Carrier threads are the real threads. JVM manages with if some virtual thread blocked, it just picks another virtual thread, mounts it over a carrier thread, and this carrier thread is, or doing the job. And when the job is over, gives a room for other virtual threads. For join pool is used for that. And once again, I told you internally it's implemented by a structure called continuation, which is like a small snapshot of work which is happening in the real thread. And yes, as you saw, we don't use this 2 megabytes of threads. We're just starting a thread. We're just reusing the threads which are in the pool, and we are not like starting and stopping them. And the switch happens not in the operational level system, operating system layer, but in carried by our JVM itself. So there can be million of threads. They're always daemon threads. Yes, and they have a special group which is called virtual threads, and no permission to work with security manager, but it's deprecated anyway, so we don't need to care about this. So there are just small changes in the API itself. Means that we have a new function like new virtual thread executor. We can start a virtual thread or a task, make it off virtual. Again, what is awesome that now as we have this resources as extremely free, I would say, we can just pick a job, start it there, and throw it away whenever it's done. We don't need to care about mounting, unmounting, etc., etc. So, and yes, here was a little bit the theoretical part. It means that we know that now we have this construction, and this is good. By the way, there are a lot of talks, I believe, on some dialogues talk, which in detail tell us what happens inside of those virtual threads. But now that if we take, if we use parallel programming, here we'll just make a small remark. If we use a parallel programming, and we know how many cores of CPU we're running, it's cheaper to start a normal thread over a core than to start a virtual thread over the same number of cores. If you have thousands of threads, then yes, you have to go virtual threads to let JVM manage it. If you have several threads and you manage them yourself, then it will be much less expensive for you. Once again, virtual threads are technically more expensive in terms of memory than normal threads, but when there are a lot of them, this is beaten by the better usage. So, and you will ask, where is the action part? And yes, exactly. Here I come to the Helidon, which I was working on and still, big enthusiast on. And here in this small framework, we actually managed to use them like in real life. And just to make a small introduction, what is it? So it's a framework for developing microservices, of course. It's a server, but not a server container. So yes, we do follow some standards. I'll show you later, but we're not serverless container. So it's not a full Java EE or Jakarta EE machine, which is very heavy. No, we're extremely lightweight. And yes, the main idea is to depend as less as possible on other frameworks. Yes, so technically we are competitors to Quarkus, we are competitors to Spring Boot, we are competitors to Micronaut, we are competitors to other such frameworks. Yes, and what is good about us is that we don't have so much dependencies. That means we are better for security, we are better for bank usages, for example, for usages in security storages, etc., etc. So yes, once again, the idea is that we have to be very simple. We don't use tricks and cheatings like other frameworks do for startup time, for compile time. No, we don't use it. We rely strictly on Java code. As we say, try not to use the external dependencies, which means that um, um, all the security, scans from the enterprise are very, very, I would say, with much less CVEs. And we always try to keep the latest version of Java, so we support LTS. Our big releases are bound to LTS releases. So that's why we are very, very much easy in adopting the latest Java features. Yes, as you see from this small picture, I'll be quick here. So Helidon 1 was Java 8. Helidon 2 was Java 11, which means that we were modular by the very beginning, so we used the modularity. Now Helidon 3 was Java 17 with all the features that came Java 17, like records, like text blocks, like a lot of that stuff. And we moved to Jakarta namespace. And now in Helidon 4, which was released, it's 2023 actually, 2024. It was last year at the end of the year. We are now bound to Java 21 features, so it's the minimal version that you have to run is the Java 21. And this, as I told you, we're using the latest and greatest stuff. So that means that our packaging is not just an executable jar, as you can see here, but you can also create a custom image. Since I told you we are modular, there's a custom image of your application by just throwing away all the code you don't need, or you can create your VM native image. We are very much friendly with this. I believe we have the best support of application. Practically all the application can be built in native image, which makes it extremely fast. But here comes the interesting part. Helidon itself was designed to work on different environments. So one of the environments was I would say just a normal environment when you create an enterprise application and it doesn't run too much fast. In your case, this is your right side, and this is called Helidon MP. MP is because we are following the micro profile. I'll tell about it a few slides later. As a standard support, it means that our code is standard, so you can drop in any micro profile code from other vendors. For example, you want to migrate from from Tommy, from Open Liberty. You just drop the code and it works because it's standard. And it's just with some annotations, which is the magic, which is very string-like, string mimicry here. Then next thing is that. For special operations, as we call, when you don't need all of this overhead and you need just the performance, we have the Helidon SE, which is fully functional framework with the idea that it should be extremely fast and extremely transparent with pure Java with no magic. So as you see on your right, there are some annotations. On your left, there are no annotations. You write pure Java code, and it's very fast. So technically, you can see that we previously were based on NetT until version 3, which was the de facto standard, and NetT is asynchronous by its nature. So around this, we built this Helidon SE, which is also reactive and asynchronous. And on top of it, we built this blocking API microprofile model. So as I told you, Helidon SE is a smallest part framework. It's like a wrapper libraries over NetT, with the most idea to be reactive, to provide you reactive streams, to provide you all the infrastructure with the completable future available from Java 8 plus, with the biggest idea that it's non-blocking with back pressure, and yes, it's designed to work in very, very heavy duty environments. So to make this possible, we have created our own reactive engine. It was contributed by David Karnak himself. So we have this reactive operators like multi and single. If you have experience with Spring, you know that it will be like mono and flux. But what makes us quite unique that we build this not on some constructions that we imagined, but we built it using the Flow API available to us from Java 9. So that means that we are also standard here. Yes. So as you see, there's a typical code like multi, just do something with a stream of data, like limit them, map them, make it for each add a sum. That means that here we reactively work on a stream of or some set of information. If it's only one piece of information, then we just use single. So yes, I once again won't dive too much because it's we don't have so much time, and it is that yes, we had to be reactive to withstand the highest pressure. But then we have built our own engine with our own set of reactive operators. Yes, it's not that big and long as, for example, Project Reactor or RX Java, which are separate projects mainly using the Spring World, to actually give us way to manipulate this data. But we only need flat map and collect to do the most stuff and maybe reduce. So yes, there is a reactive engine, and this reactive engine is quite good. I'll be honest. That means that sometimes we're twice as fast as other frameworks. So it's really highly efficient. Yes, and on top of it, we built our own web server. Web server to create and start. It's completely asynchronous. And this completely asynchronous, server is you just start it, you write your applications there, you write your code, and it works. It's a pure Java. You see, just the main method. The only actually problem here is that once you get reactive, you always have to be reactive. So that means that you cannot make blocking operations inside of reactive operations. So as a good example of blocking operations are the database calls. And for that, we have created our own DB client, which was actually like a wrapper working to make, synchronous database calls, because most of the drivers are synchronous, asynchronous to convert them to a synchronous way, to create a synchronous wrapper over them, because then we just run this code in a separate executor and we talk to it in a asynchronous way. It's the same for web client. If we're consuming some data from other services, like calling some other endpoints, the calls are also asynchronous. Yes, but what we know that reactive programming is extremely hard. So it's very hard to debug. It's very hard to write. It's very hard to actually achieve this performance, because once again, in conferences or in talks that may sound easy, look, I just write some operators and it magically works. The real life have shown that this is a very hard code, very hard to debug, very hard to learn, very hard to read. Not even write. Sorry for that. Not even write, but to read it. So yes, it is what it is. So, and by the way, I'll just show you that you can create your Helidon applications. Just go to helidon.io, and there is a very nice start there. And here you see when you run, you can just create Helidon SE application or MP application. We were talking about this SE, where you just make a quick start. It just creates a zip file for you. Nothing too much special. Oops, sorry. Nothing too much special. It's just POM file with all this stuff. And if you go to the sources, you will see that it just have a main class, which is nothing too much special, which runs our server. And the awesome, framework details, like for example, a greeting server, which implements an HTTP server interface, which we made with the idea is that you have server request and server response, and you do something with it. It's so much easy. But this is the way you create your Helidon SE application. Once again, I would call it a special purpose operations, because it's extremely hard stuff to do. Yes, and for this, actually, we have created a wrapper over it. I would say another layer over it, which is called Helidon MP. And MP stands for microprofile, which means that this is like a set of specifications to write microservices. Um, yes, it has something in common with Jakarta EE. There are some core APIs which are like intersection from both worlds, but still, it's not yet another Jakarta EE. It is a special microprofile set. That means that it's a special set of operation which is designed for microservices world. And as we know, that microservices are typically something which is like a good example of a distributed system. They can fail unpredictably. They need to be monitored. They need to be observed. They have to have um, security, which is like spread across multiple instances. And this set of specification actually regulates all of that stuff. And here we decided that we will wrap our Helidon SE into this specification. So out of the box, you get everything what you need to run the microservices. You even have standard configuration like tracing, like OpenAPI, health checks, metrics, even some standalone specifications like GraphQL, like implementation of the Saga pattern, which is called LRA, reactive stream, and so on, even more. You even have the data persistence there, and gRPC calls like WebSocket, like everything you need. Yes, but and what we're really proud of that you have a full CDI specification which is able to run in native Chromium native image. I think that nobody has them still, but it has a very big problem. By the way, if we go back to Helidon Starter and just create another application, which is MP application, I'll do the same. It does absolutely the same greeting service. So yes, you will see that the code itself changes a little bit. So whenever you don't have a main file, but whenever you have some kind of resource, you will see, just let him, yep. You will see that it has some annotations. It has some get, produces, all of that stuff. It's very Spring-ish stuff. So we achieve the same result, but actually adding with some annotations. But it has drawback. It means that you will need more time to start all of that stuff and to run. So we kept the two products actually because there were trade-offs. One of them, you have to be reactive and have a great performance with high concurrency, but it's hard to run, it's hard to read, it's hard to write, it's hard to debug. Or you have a standard way, which is Helidon MP, which is easy to create, easy to write. You have a lot of trained professionals who actually do this stuff. But by the main concept, it is blocking. That means that whenever you have a call or something to a database, it simply blocks and waits for this call to be done. So this is the trade-off. So either high performance and complexity or simplicity, and I would say an average performance. Yes, what is the idea? And here we come to this the specifics of this framework. So actually, to create a framework, which is a server, to add more performance, you really need to add more threads. You simply need to scale. And here we actually are found that Helidon plus virtual thread is the perfect match because, once again, you have a lot of threads, each serving each request, and you don't have to manage them because JVM will manage it for you. So we decided to create from scratch a fully virtual-based web server, which is called NEMA, which is now called Helidon Web Server because NEMA was a code name. NEMA means thread in the Greek language. So, and as a result, we saw that actually it does work. It does work very good. And thus we created the first framework based entirely on the virtual threads. So it has the scalability of asynchronous model with the simplicity of synchronous code is written there. So here in Oracle, we had a little bit cheating is that we were very close to the Java team itself, the Java core team, so we help each other. And as a result, we have this web server, and we really just throw away netty at all, and we have created our own virtual thread-based server. So what does it do? It does support all the HTTP 1.2 protocol, out-of-the-box gRPC, WebSocket. It has very good integration and testing framework because we were able to do it from scratch. We know the experience, and we did it the right way, not with a lot of legacy code. Of course, TLS and MTLS, and it's very much extensible. And the server itself has all this access log. It has core support, static content, of course, all the observability features like open telemetry and all of those. And yes, what is actually good here, what we say in action, that the virtual thread have are the perfect combination for our workload. So we are perfectly good for blocking code. We use a lot of new features like enhanced switching, like sealed classes, like logger. What the idea is that virtual thread are the perfect match. And you will actually say that many threads, not threads, but frameworks also declare a support of virtual threads. I'll try to explain now the difference between virtual thread support, and to be virtual thread based. So what was previously, how it was before when we were using reactive programming to make this work. So here are some, these cards are some tasks and jobs that we have to run. They're coming like multiple of them from the left side, and we have in this option only 2 threads. So what happens is that, for example, we take a task which is very fast. It goes like read params, prepare a statement, and then they make, by reactive way, they make a callback and pull other tasks, like for example, persist to DB or call some other function. And these tasks asynchronously, they are blocking tasks. That means that whenever they are done, they will pull the other task, but now they fully occupy the thread. And for example, when this blocking task is too much, waiting, we offload this task, and we call other jobs to actually call the other jobs to be done. So that means that I can't explain it in 2 seconds, but a lot of magic is happening in this reactive engine to make this work and to make the gaps between tasks very, very small. What is the Helidon doing after we introduced virtual threads? As easy as that. You have several requests. For each request, we just create a virtual thread, and we let the virtual machine actually manage the stuff. For example, when a request comes, so we have only 3 threads working here. All these threads which were not able to find their processing time, they're just stopped, and they are waiting to be called. You see, well, for example, this make IO operation in the second thread is very much blocking. So we come here, we know that this virtual thread gets blocked because JVM manages it for us. So we go to thread 4 and try to use the resource which was dedicated to that thread 2 in some other way. Okay, we hit some blocking operation thread 1. Okay, we just schedule another thread. In our case, it's thread 5 to do the job for us. And this way, little by little, you see, we are able to process all the requests. And as a result, it's very, very easy. And that's easy not just because we're really short of time, so I'll try to be fast here. The main idea is that not only the core part has changed, but the way that we write the code has changed a lot. So these are 2, I would say, the same operations, which we had to do in asynchronous way, reactive way, and totally synchronous way. I would say the new way, the old new way of doing stuff. So if you do this in a reactive way, you have to do it with all of these constructions like multi-range. You can think about it as a flux range. Then you do some flat map operation over creating a completable future, which asynchronously call as a client gets it result, and whenever the results are there, we call this flat map with some function identity. We have no idea what is it, but the guy who wrote this code, he took him about half an hour to understand it as well. Then after we made this call, like, asynchronous call to multiple clients, we can collect them to list and then, get all back, map it to a list and then return it. And if there is an error, we have to gracefully cure it because exception may happen and we have to gracefully, handle these exceptions. And then we just set the results whenever the results are available. It is very hard code. And what we do here, I believe that if you are, interested in programming, you can read this code even if you are, I don't know, in 9 year of school, because this kind of code I wrote myself when I was in the 9th grade of school. So we just start some virtual thread executor. We create some futures, futures. It's like, you write the code, you wrap it in a future, and then you wait for the result. And here, so we just send some requests to our clients, get the result as future, and then what we do, we get the responses back from the parallel calls. And what is interesting here that you see this future get, and you know that get is blocking operation. That means that whenever we come to this point, it will block the thread it is running on. And previously, we have to wait for each thread to get the result. Now, it's not over there. Because we're virtual threads, we let the virtual machine manage this for us. So this will happen in parallel way, and JVM will manage which thread to give its carrier thread to do the job. So, and this code is much more easier in terms of understanding than this I would say reactive code. I'll skip the demo for now because I will just paste or send the link with example on my GitHub so we can take a look. It's very good and easy. So, and you try to understand, okay, why is it important? Because now we pay for everything in our clouds. That means that every waiting is paying now. That means that every gap itself is, you have to pay for it. And here we solve this result. So what does that mean? That every blocking application, which is in our case microprofile application, will migrate to non-blocking way of writing code with absolutely no changes. And you will see in the demo that I'm going to show you that it really runs much faster because we really utilize the results better. And once again, we have the reactive performance with blocking code. As a result, there's some graphics that we see that if we compare it to Netty, we're even higher as results. And if we compare it to Helidon MP, which was based on blocking operation over Netty, and now we switch to virtual threads, the performance is magnitudes. And actually, let me show you this small demo. So, by the way, this is the example from the previous step. I'm really not going to show it because we're short of time, but I will give it to you, and you will see that, for example, there is. Oh, okay, I'll show you a little bit. This is a reactive call of movies database, and this is a blocking call, which is absolutely the same, and the code runs even faster. And here, just to show you that, for example, we can run million threads and our JVM will not crash. I created a small function, like a lot. It's called, here what we see, we here do the most bad way of doing count because we implement increments operation in a separate thread. Because we have millions of threads, we can do it much easier. So now if I run this code, so it's java -jar target Helidon for movies jar, you see it started in 37 milliseconds, and we do curl like a lot. What we have, a million. And you see what happens here. Here we just started a million virtual threads, and did the increment operation there, and then we just simply throw them away. And you see, we're doing the presentation, I'm talking to you, and we started a virtual threads. They started in milliseconds, and we are still able to do our job. So yes, these resources are much more cheap now. And now, if we switch to this example, which I prepared for you, which is actually our example from our good colleague, Thomas Lange, my ex-colleague now. What does it do? It simply demonstrates what does mean blocking operation for us. So we have a server which have two endpoints. One endpoint is slow. What does it do? It gets a request, then just sleeps for some time, and then it gets done. And we have a quick, which simply returns done. The idea is that if we have a small set of processors available to execute this resource, in our case, I believe we have about 10 processors or something, 10 threads. We simply made them 10, like with this configuration property. Yes, the pool size is only 10 threads. Whenever we have several requests, this long requests, where is it? Yes, slow request will simply sleep and block our requests. And the quick will be just return error because they cannot get through this slow requests. The very same is done with a reactive way, and we will see that. I don't go much into details how it's done, but we can achieve absolutely the same result with quick and slow endpoints by the idea that now, as it is reactive, we can see that how this reactive engine manages all for us. And now you will see the difference. So I will go to terminal. I will start several Windows groups. And I hope you can see them. So we will start our server as no room. So the server has started. And now here is the interesting stuff. So we start our slow polling request. Java-jar target client something. It will start polling our service and it will get some requests. And now if we start our quick client, Java-jar target client something, you will see that we cannot break through those sleeping requests. So we have 10 requests which are sleeping, and here we get errors because we simply cannot process it because it is sleeping. And if we get htop, we see that our processor is not utilized at all. It's simply sleeping. We are waiting. We are blocked. Yes. And now, if we stop this thing and return our and make our server the same reactive in a reactive way, it will do the magic for us. You see, immediately we can have our sleeping operations, and then we are able to process our quick operation. And you see how the htop says that our processor is now utilized because reactive web programming helps us to small by the callbacks not have this sleeping gaps in our processor. Okay, so I will just stop it for now. And I'll put the htop here. Yes. And now here is the most interesting part. Now we have our blocking application written in a blocking way, but with Helidon 4 server, which is based on virtual threads. And now if we start this server, you will see that, okay, remember when we started this no loom server, it gave us this a lot of errors. Now, as virtual machine actually manages those virtual threads for us, we have the performance which is comparable to reactive and maybe even faster. Now it will, you see, it will warm up and get better result. So that means that now that virtual machine is managing our threads for us, and all the gaps, everything which is blocked, the virtual machine pulls it out of the code of the carrier threads and assigns another virtual thread to be working on it. And here is the main magic. Here is the virtual threads in action, which actually does all this magic for us. Okay, I will stop it for now. I'll stop this for now as well. Stop this for now and stop this for now. As easy as that. Okay, let's go back to the slides actually. And no, not this, but this. So what is the problem? If you start, for example, crypto mining or video encoding, you will obstruct the thread. In our case, we don't obstruct. Our operations are very short and they're not blocking. And this is why we are the perfect match for this virtual threads operations. Yes, which is completely awesome. Yes. So what were the challenges actually that we had there? Is that the main actually idea is that in our mind, we're started thinking asynchronously just because asynchronous, as our mindset, was providing better performance. But no, not anymore, because virtual threads are managed by JVM and we don't have to think about it. We have to unlearn asynchronous and start making back blocking stuff, and it worked even better. Yes, the best performance achieved not with asynchronous sockets, but even with blocking sockets. That means that that was the most hard part. We were starting to write asynchronous code, but it was wrong. We had to block, and the virtual threads will, JVM using virtual threads will do for us, and thus the code becomes much easier. And so the only thing we have to know is that there are situations where virtual threads are not unmounted from the carrier threads, or some OS limitation. For example, if you use object.wait, it will not unload from carrier. So then if something is not uploaded, the JVM will add temporary threads to our fortune pool. Yes, the other situation when you are pinned to carrier is that you use the well-known synchronized blocks, our native methods. Yes, which is you have to still rewrite some code, but if you're using the Java util concurrent collection with reancient lock, with other locking operation, then you will have the maximum performance, and then you won't get pinned. So once again, whenever you're using virtual threads and you don't want to be pinned, you have to use Java util concurrent stuff. So, and what are the ideas and what we learned from using virtual threads is we have to unlearn asynchronous programming at all. We had to refactor from synchronized to Java util concurrent. The only thing we have to think about is the thread locals. Yes, thread locals are actually available to us. You can use them, but if you have millions of threads and you have millions of thread locals, then you get out of memory just with this thread locals. And now there is another gem which comes. It is already preview feature in Java 20. I believe it's starting from Java 20 about scoped variables. And the scoped variables are exactly the solution to this problem. And there is a structured concurrency, which is also a preview feature, Java 19. So yes, and what is the best thing is that we have this Java 4.4.4, which means that virtual threads are already available in Java 29, and you can use them as we do. So that means that if we have to choose now between high performance and complexity, and simplicity, we don't have to choose anymore. We have both simplicity and high performance. And this is available for Java 29.1. Just simply to upgrade the system to Java 21, and you can use Helidon with this. So what does that mean? Virtual threads, and with Helidon as an example, so we offload all complexity of writing this reactive asynchronous code, whatever it is, to JVM. We don't have to do it. We just write very straightforward code, and we have a lot of performance, which comes back to us. So what is good here is that if we take the threshold performance result, we are mostly using this Tech Empower as a benchmark. We see that Helidon outperforms other competitors which use asynchronous or reactive engines underneath. So that means that the code is much simpler. By the way, what is also good, the code base of Helidon has shrinked like 3 times because we have thrown away all of this reactive, code, which was extremely hard to write, maintain. With all this, I won't tell you how complex it was. Now it's like in school, you write very stupid, programs, and they run fast, right? Really fast with this. So, and once again, so this was exactly the idea is of that. Yes, Helidon actually uses those virtual threads. So we have them in action. You see the result. You see that virtual thread are the game changer. And here is a very nice applicable case of using virtual threads and real, software, which is open source, by the way. If you want to learn about Helidon itself, the best part, of course, is just to use the GitHub here. You have Helidon. It's not IN, it's IO. Sorry, my bad. Helidon IO. It's not IN, it's IO. You just go there and see the code, and you will be surprised how simple this code is. That means that you can just start a socket in a blocking way. You write your output or input from this socket. So get the input from this socket, you write this output from this socket, and you just get the result back. You don't have to have this reactive engine, which will get you all the callbacks, etc., etc. Simply go to this URL, and you will see how easy it is. If you have more questions for a lot of social networks, you can write us. And there are a lot of YouTube videos also recorded by me. So when you can see all this result, and I believe that the team is constantly monitoring Stack Overflow. So if you have any questions for that, just let us know. Once again, we have really, I'm 10 minutes over the time. I really want to tell you more, but to tell you more about all the internals which happens there, it will take like several hours. Maybe someday I will come to Riyadh and we can do it offline together with you. But this is like an introduction how we use virtual thread and how this virtual thread actually changed the world. So with this, I want to say big thank you for having me, and I really hope that you enjoyed this this talk, or at least you have this small lamp over you when you start thinking about, okay, virtual threads, okay, we have them in Helidon, we have to see how they did it in Helidon, and we can use it in our software as well. So thank you so much. I don't think we have time for questions, but maybe 4 more minutes. I'm with you to answer your questions.
Yeah, thank you so much, Dimitri, for this amazing presentation, amazing talk. Thank you so much. There are some couple of questions, if you don't mind.
Yes.
When deciding how many threads to use, should we use the normal threads for small number and for the virtual threads for like large number of threads? Is it like is the
Yes.
case?
Yes, exactly. So you see, virtual thread has some overhead over the thread itself. That means if you take a look at the structure of of a thread, so we have a normal thread, and then you have a little bit overhead for virtual threads. That means if you have only 10 or 20 of them, you still have more overhead you don't need. Um, you know, when you have massively a lot of threads, massive amount of threads, then comes the part when all the switches between threads will take more time than all this overhead carrying for continuations, which I showed you. Uh, this is the most important part. So for small amount of threads, just use normal threads. For huge amounts of threads, I will say a good example here. As far as I remember, on a normal machine, you can start up to 400 threads, like server machine with 32 cores or 64 cores. You can start 400 threads, and it will be okay-ish. After that, all this garbage collection will happen, all this management will happen, so you will lose a lot of resources there. So after that, you just switch to virtual threads and you skyrocket everything. Yes, this is the answer to the question.
Yeah, that sounds really good. Sounds very good.
Mhm.
Second question, if you don't mind, like, is Helidon compared to other frameworks like Micronaut, Spring, etc., Quarkus?
Uh,
So we have now several of frameworks in the
yes,
industry. So what are, from your experience, what are the best use cases to choose Helidon?
yes. So Helidon, just to let you know where is it used and why it's good. So Spring, let's be honest, Spring is huge. You have a lot of libraries working with, you have a lot of integrations with Spring. That means that whenever you are, for example, creating a huge infrastructure for, I don't know, banking or something, you need to work with a lot of databases, a lot of caches, a lot of, um, mm, you're connected to too many systems. Then yes, you have to choose Spring. Um, Quarkus is good because it is competitor to Spring. It also has quite a big ecosystem, which is smaller than Spring, but it's growing, I would say. Um, and the idea is that it is micro profile as well. That means if you need to migrate your application from another server, like Liberty, like WebSphere or something like this, you may choose Quarkus. Then you don't have to rewrite the code because it's micro profile, it's standard. Uh, but it has this performance stuff, so it's still reactive. It still depends on many other libraries and so on. So Micronaut is like somewhere in between, because Micronaut is cool for the compile stuff that happens. It does a lot of stuff compile time, so it's better for a start, and it still has a good ecosystem, and it's very much, I would say, allied with the GraalVM because it's actually the same team who's working on it. And here comes the Helidon. And Helidon, it is very pure. It has less integration, less third-party code, which means that if you need to create small, very much performant microservices, Helidon is your choice. Because, as I told you, we almost don't have any third-party dependencies. That's why many banks choose Helidon because it's secure. It does not depend on anything else. For example, if you take a look at the booking, there is this Oracle hospitality stuff, which is actually in the core of booking everything in this world. Booking hotel, booking hospital, booking ship, booking, I don't know, car. It all goes through all this Oracle hospitality stuff. And it is based on Helidon. Uh, Previously, it was based on Helidon Reactive. Now I think they're already moving to virtual threads. But it can handle millions of operations in a second, and it's very, very small. I know that something which was based on reactive machine is 17 megabytes per microservice. It's so much scalable, and now as they move to virtual threads, they can much easier write code because it's once again microprofile. And if you have microprofile applications, which is comparable to Quarkus, for example, and you don't need this vast integration ecosystem, you write a pure microservice which gives you JSON or something, Helidon is definitely of the choice because it's much smaller, it's much securer, and exactly as I told you, it has the performance of a blocking, way of blocking style with the reactive performance. So as easy as that. So this is, I believe, the main advantage of Helidon. I hope this
Sounds
answers the question.
yes, it does. Sounds very, very promising and challenging and really nice.
Yeah.
The last question, if you don't mind,
Yes, of
are
course.
there any performance metrics comparison between these projects?
Yes, as I told you, on the slide, there is this Tech and Power benchmark. So it's round 22. Most probably there are many other rounds. So if you go to Tech and Power, uh,
Can you
yeah,
please share your
benchmark.
screen if you don't mind?
Sorry.
Yes,
Yes,
sure.
sorry. Uh, every time I forget to share it. Yes, present screen and entire screen. Yes, not this, but can you see it? Yes, can you see it? Hello?
Yes,
Okay,
yes, I can
maybe
hear. Yeah, yeah, I
yes,
can hear. Yeah.
yes, you are dropped off. Yes, and so there is the screen. So this is the official something. And if we go to Tech and Power, so there are some different rounds. Now when we take the previous round, which was the previous year, now this year will come. And here you have all the frameworks which are in comparison, how they do it, how they do it the right way. And yes, so they are for JSON, for example, for single query, for multiple query, and you will see where is Helidon, let's see, Helidon is here, but compared to uh, Vertex, for example, which is different stuff. And Helidon is good because it's micro profile, and Vertex is pure Java, I would say. So here you have all the trade-offs, and you can see it in this result. Helidon, for example, which outperforms everybody in Java world. Still, yeah, you can see it here.
Amazing. Yeah, that's amazing, amazing. Thank you so much, Dimitri. Uh,
Okay.
yeah, thank you so much. Please, if you can share us also this presentation later in the email, then I'll share it with
Yes.
the community. Thank you. By with having this said, thank you so much, Dimitri, for this amazing presentation. Thanks, audience, and looking forward really, really to see more talks from you, Dimitri.
Thank you so much. It's been an honor and pleasure. And I really, you're a very young community, but you still have so many people. I really wish you grow fast, and we'll always help you as much as we can. And thank you for having me. It's been an honor. And maybe someday very soon I'll visit your country, your beautiful country. Thank you so
Yeah,
much.
sure, 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 sure. Thank you so much. See you. Good
Bye
night.
bye.